We will allow questions only through the chat and they will be answered after the talk. Dr. Giuliani, can do you want to tell an introductory note about you, or do you want to proceed?
It's up to you. It's up to you.
Okay,
I can introduce myself.
Tell 1 minute. 1 minute.
Sure.
Introduction.
No problem.
Okay, thank you very much. Dr. Gregory Giuliani is the head of the Digital Earth Unit and Swiss DataCube project leader at GRID Geneva of the United Nations Environment Programme, and a senior lecturer at the University of Geneva Institute for Environmental Sciences. He holds a Bachelor of Science in Earth Sciences and a master degree and PhD in Environmental Sciences. Gregory's research focuses on land change science and how Earth observation can be used to monitor and assess environmental changes and support sustainable development. Interdisciplinary is a key element for generating new ideas and innovations in his research. So, Dr. Giuliani, the floor is yours.
Thank you so much. Good morning, everyone. That's a great pleasure to be with you today and to have the opportunity to give you this presentation. So I hope you all see my slide and not the handout, because I have two screens. So just to be sure that you have the full version of the presentation. So thank you for the nice introduction. And through this presentation, I would like to show you how in Switzerland we've operationalized this concept of the DataCube technology, and how we are moving towards also the idea in terms of research of enhancing this kind of open and reproducible science approach. So you will see that all along the presentation. But basically, to frame a little bit the presentation, I think the big challenge currently that we all face in the environmental science, I would say broadly, it's to build policies based on scientific evidences. And all our work is going in that direction, I would say, in that frame of this data, information, knowledge pattern. So basically the data is any type of measurements made out from satellite, in situ monitoring stations, citizen science observations, or field research. Then when you structure this data under the form of a map, a graph, for example, then it becomes an information. And then when you contextualize that information, it becomes knowledge. So you have an explanation showing, for example, the graph of CO2 concentration above a given region. So you can explain why there is an increase in terms of CO2 CO2 estimates. So we can say that thanks to that, then you can build an understanding on a given situation, and then hopefully you can take sound decisions to manage the environment. So in summary, we can say that the knowledge is informing us about the limit of the planet, so the limited resources, and then the actions, so the decisions, is how a society or the societies more globally decide to use the limited resources of the planet. So to understand all these changes, you know that since the early 70s, so more than 50 years ago now, the Earth is under continuous observation from satellites. In that slide, in that animation, this is the current fleet of satellites operated by NASA. And if we look to the Copernicus program, so the Earth observation program from Europe, so led by the European Commission and the European Space Agency. I think you are all aware about the Sentinel-2 satellite. So it's taking an image of a given region on the Earth every 5 days. So it means that it takes more or less 22,000 images to cover the entire planet. And it takes, in a year, something like 1.5 million images of the Earth surface for this single satellite. So if you look at the entire fleet of the ESA-operated satellites in the frame of the Copernicus program, you see that clearly the Copernicus program is the largest EO data provider in the world, with an archive that is around 250 petabytes of data, and the daily growth rate is around 200 terabytes, something like this. So new acquisition every day. So you have 200 terabytes of new data coming to the users. And what is interesting also to see from the past, and specifically also looking at the Landsat program, so the US program, since 2008, you remember that now it's under a free and open access license. But before that date, you had to pay to access the data. So you see that it was a clear issue impeding the access to the data. But now, thanks to this open data license, everybody basically is using Landsat data around the world, and we can see similar patterns for Sentinel data, MODIS data, and all the different types of satellite data that are freely available. So really, this is a big incentive also in terms of open access. So we can say that basically, if you look also at Landsat and Sentinel data, so if you make a synergetic use of these two sensors, we can really monitor in near real time the Earth's surface. So that's a big advantage, but obviously it comes with big data challenges. So as you imagine, the data volume is a big issue. We are talking about terabytes of petabytes of data. The variety or heterogeneity of the data is also a big issue, because you have the different types of sensors, different types of optical sensors, but also different types of sensors. So you can have radar sensors, LiDAR sensors, optical sensors that have both all different spatial, temporal, and spectral resolution. So it means that you have to handle this heterogeneity. Then obviously you need somehow scientific understanding to know what type of data you need for which type of analysis. But usually we say that accessing and downloading this data can be quite difficult. Let's say if you go on the Copernicus hub, it might be a little bit slow to download the data. Then once you have the data, usually maybe you have to prepare it, so do the atmospheric correction or the speckle filtering if we are talking about radar data. So it means that you need some capacity building and training activities also to handle this big data, big Earth observation data. And I think really the big challenge is, if we think about this data information knowledge pattern, it's how we can transform this really large amount of data in something useful to inform the decision maker and support them with scientific evidences. Sorry. So the traditional way we used to handle satellite data, I think you are all aware of that, but basically you go on a platform, you identify an area of interest, then you send a query to search different catalogs, you browse among millions of scenes, petabytes of data, then you refine your requirements according to the cloud cover, for example, and then you come with a subset of interesting data that you download, and then you pre-process. And then at the end, you can start really doing what is interesting for us, I would say. It's doing the scientific part, so the analysis, developing new algorithms, new application, and then package the output in something that is an information product delivered to the decision maker. So the good news is that the entire, I would say, blue area can be fully automatized, so that we can really concentrate on what we want to do. So basically data science. In the past, we had to invest in the entire value chain, from the data acquisition, I would say, from the data portals up to the packaging of the information product. But now with the data cube technology, what we can store into a data cube, and this is the point where we can automatize some of the process, is that this raw data up to the surface reflectance process, this is the analysis ready data production process. This is what we store at the end in a data cube. So it means that as an end user, you will see analysis 3D data. You can directly start working with the data without any further pre-processing steps and so on. So you really reduce the burden for the data user, and you spend much more time in doing scientific analysis. So in short, a data cube is a time series, multidimensional, both in space, time, and also data type. And this is a stack of spatially aligned pixels that we can process efficiently and effectively through space and time. So we call this technology data cube because you can sample the cube in the different dimension. So if we take the last time step over a given area, we have a traditional satellite image, traditional satellite scene. Then if you aggregate through space or time the data, then you have a mosaic. And then if you look at the variation of a pixel or a group of pixels, then you access the time series analysis, such as the lens surface phenology. And if we look at the national scale, I take the example of Switzerland in our case, but I think we can easily extrapolate to all countries around the world. We can say that the governments, they all have national and international reporting commitments. They need information that is synoptic, spatially explicit and consistent so that we can capture the environmental changes, mostly caused by anthropogenic impacts. So it means that this data cube technology can at least contribute to support that vision, because it provides this long baseline to determine the trends. So looking at the past, basically, then you can define the present situation. So you can look at the status. And then if we inject the data or the outputs of some remote sensing data into models, then you can explore different futures. So it means that, yeah, that's a tool that looks quite interesting in that frame. So in our case, in Switzerland, we started back in 2016-17. The Swiss government approached us, so the Federal Office for the Environment, to test this technology. And now it's fully operational at the national scale. So the Swiss Data Cube is a GRID Geneva and University of Geneva product. And we signed a memorandum of understanding with the University of Zurich and the WSL, that is the Federal Office for Snow, Landscape and Forest Research. So it means that currently in the Swiss Data Cube, so we are updating on a weekly basis the data cube with the new satellite imagery. So we have the entire archive for Landsat 5 to 9. So we have the latest sensor into the data cube for the last 38 years, plus the entire Sentinel 1, 2, 3, and 5 sensors. So it means that we have 10 sensors into the data cube, but we also ingested other types of data. So we have now official governmental data, such as climate model from Meteo Suisse, the land cover data sets, the digital elevation model, and much more. And we complement that, and you will see also at the end of the presentation, we have an additional database of Earth observation data product. So we generate on a regular basis and on request the time series of NDWI, of NDWI, of LAI, and other vegetation indices in that case. So it means that currently we have more or less 30 terabytes of data ready for analysis into that data cube. And the two interesting number, I would say, is the first one is related to the pixel. So if we say that a pixel is similar to a ground observation, we have more than 3,000 billion observation of Switzerland stored in that data cube. And if we think about the open data access policy, if we had to pay to access this data, like in the past, it's around 40 million euros, because we had at the parity with the Swiss franc, 40 million euros just to get the data. So it's a big treasure also of data stored into this data cube. So we have many ongoing activities. So in terms of environmental monitoring, and I will show you some examples, but we are supporting national and cantonal monitoring, so the subnational level, mostly looking at snow cover evolution, the impact of the recurrent drought that we have in summer on vegetation and rivers. We are also looking at air quality monitoring and so on. We have also dedicated activities related to the Sustainable Development Goals. So, for example, in terms of monitoring land degradation or the urban, also green areas in cities. We have many collaboration at the cantonal level, at the national level with the different departments, at the international level. We are collaborating with many countries, and we'll be more than happy to work with you in Cyprus. But also we are collaborating with the private sector and also the research field with different universities. And we had, as you can see, currently we had already more than 25 scientific publications. We gave more than 60 or 70 presentations on the Swiss Data Cube. And we have many other things. So I will show you in a moment what we have done concretely. But really our vision is to provide an infrastructure that can provide reliable and operational services based on satellite Earth observation data, so that we can deliver what we call decision-ready product to the policymakers. So this is really our aim. It's to provide insights for action and trying to see how the Switzerland's landscape has changed over the last 40 years, let's say, basically. So really our mission in terms of infrastructure is to provide that infrastructure based on free and open access data. And we are working with different communities of users so that we can help them in understanding the benefits that you can have from satellite Earth observation data, but also the limitation, because obviously you cannot do everything with satellite imagery. And we are really aiming to deliver a kind of capability to track these changes and see the evidences of the changes in Switzerland. So the technology we are using in the Swiss Data Cube is similar to the one used in Australia. So this is from the Digitalis Australia. So this is the Open Data Cube. So it is an open source project that is led by many agencies, and we have a big community of developers and users. But in short, the Open Data Cube, this is a Python library that allows and facilitates to work with satellite raster data, let's say. So if we look quickly to the infrastructure itself, basically, so you have a tier where you store the data. You can store it as native file, or if you have the chance to have the equivalent of S3 Amazon nodes, you can store the data in these nodes. This is what we are currently doing. So we are moving the content from a native file system to the S3 Amazon cloud nodes that we have at the University of Geneva. Then you have the data cube itself that is indexing all the data into a database and providing a set of application on top of that based on the Python API that you can access directly through Jupyter Notebook. So these application where you can remotely access to the data cube and execute portions of code. Or we have also the entire suite of OGC services, so you can also use these interoperability standards to access the data and process the data. So some examples on the use of the Swiss Data Cube. In that case, during the drought we had back in 2003, we had huge forest fire in the Alps, and you can see basically the scar in the middle of the image after one of these huge forest fire in a protected area. And then now if you look in 2020, basically, you can see that the vegetation is recolonizing this area. So this is a good sign. So vegetation is coming back. It's not yet a forest again, but at least the vegetation is coming back in that area. Another example in that case related to water. These are two lakes in the central part of Switzerland. So this is the Lake Thun on the left side and Lake Brienz on the right side. And you can already see that visually, these two lakes looks a little bit different. And if we take the data and run an algorithm that is able to estimate the content in terms of total suspended matter into the water, you can see that basically the Lake Brienz is full of sediment. And the explanation is that basically you have a river flowing from the right hand side, coming from the Alps, so full of sediment. So the river is depositing all the sediments into that lake. Then the river continues to flow to the Lake Thun. And obviously the water is, I would say, cleaner than it used when it enters the Lake Brienz. So it means, it explains why these two lakes are somehow different. Again, related to the different drought impact. So this is a small unmanaged lake at the French border. So this is the Lake des Brenets. So this image is the situation in 2017 during the summer. So it's an aggregation of all the data over the summer months with Sentinel-2 data. And in 2018, you remember we had a huge drought, and you can basically see that visually already that most of the southern part of the lake completely disappeared. So it was completely dry, as you can see also in this image on newspaper. So basically the boats, you were not able to go for sailing, basically on the lake. And what we have done, we have used an algorithm that look at the frequency of observation of water in images, and then you can compute the frequency. So in dark blue, basically you have 100% of the time water, so it means permanently watered area, whereas the other colors show you that it's temporary water bodies, let's say. So you can clearly see the dynamics of the lake drying in the southern part, and also the level of the lake that is decreasing on the northern part. So you can see the border of the lake. Another example in that case related to cities. So in the frame of the SDG, there is an indicator on urban green areas. And what we have done, we have developed a methodology using satellite data to estimate the accessibility to urban green spaces according to different scenarios of movement. So we've done that in Geneva as a first test, and we've done that also in 4 other cities in Europe. And then we extended the work on the entire country, not looking only at the urban green areas, but also green areas outside cities. And we've been able to model this accessibility at the national scale, and then compute statistics for each communes and each cantons to see how they perform and where maybe we need to improve the situation. Again, related to drought, because I think that's a big issue currently. So this is an image over the summer months in 2014 over the Geneva area. So it was in our region, it was a kind of rainy summer. So you see that the vegetation is quite green in that case. But if you compare the same area with the 2018 images where we had one drought, you can already see that the vegetation is a bit more brown. And if you compare to 2003, obviously it's completely brown. That was I would say the most impactful drought that we had over the area. So this is a visual interpretation, but then you can use an algorithm that is called the fractional cover that on a per pixel basis gives you the proportion of vegetation that is active, inactive, so dead, and all the bare soils, so basically the cities. So again, in that image, this is the situation in 2014. Then in 2018, you see already that bit more blue information in that image. And then in 2003, you see that a lot of the area was impacted and a lot of vegetation was dead. So then at the end, you can also compute you can quantify the amount of vegetation that was dead at that period. So based on that was an early observation. What we have done, we have generated the NDWI time series for the entire country. So this NDWI index is a kind of proxy of the water content of vegetation. So if you compare 2003 to 2014, you see that the vegetation was much more drier in 2003. And then due to the fact that we had the time series, you can compute the national time series. So it takes all the regions and all types of vegetation, but you can see already that there is a significant decrease in terms of water content into the vegetation. So it means that in general, vegetation are more drier than it used to be. And then you can disaggregate, for example, in biogeographical regions and see what are the differences between the Alps and the lowland, for example, or the Jura Mountains. And then you get a better view of what is occurring on the different landscape units across the country. And based on that, what we have done, because an idea that we have also is to build services not only for remote sensing experts, but also for our end users. So we are facilitating the access to that information. So we published all the data and the statistics in a geo portal, basically, where you can look at those trends, both in terms of annual change and also seasonal changes. Also, you can compare the different subnational levels, so the different cantons, both also in terms of annual and seasonal means. You can compare two dates together. So with this slider, so you can look at different dates and compare the two dates to period of time, and then you can visualize also the time series dynamically directly into that map. And we are doing that for many other activities, like also air pollution monitoring, land cover monitoring, and so on. Next example, it's related obviously to climate change. As you know, Switzerland is worldwide famous being the water castle for Europe. So many of the main rivers have their origin in Switzerland. In that case, this is the Rhone Glacier, so the source of the Rhone River back in 1985. And if you compare the same region with 2018, you see that obviously the glacier has receded dramatically. And now we have a lake in front of the glacier. And if you compare to 2020, you can see that the lake is still expanding quite fast. And as you know, obviously snow cover is a big issue in our country. Because snow is an important form of water storage. This is considered as an essential climate variable. And this can be an indicator of climate change, and it provides many ecosystem services. So what we have done, and we're currently working on that, this is one of our PhD students. So she's developing a methodology to look at snow cover and then compute frequencies across time. And for example, if you take a decade of observation over the winter months, between, in that case, 1995 to 2005, so you have in dark blue the areas in the Valais region that are famous for all the ski resorts. You have 100% of the time snow during the winter months, whereas the red areas are the areas typical from the lowland, where you have a little bit snow during the winter season. And if you compare this data set with the next decade, what you can see is that the red areas are increasing. So it means that it's going up in altitude in the valleys. It's expanding all across the country. And in parallel, the permanently snow-covered areas are decreasing. And what we have done, if you do, for example, just a difference between the two maps, then we've been able to compute and estimate the decrease of permanently snow-covered areas that are about 4% for the last 20 years, whereas the increase of these red areas is about 8% of the area. And then, because we can disaggregate at the pixel level the information, then you can identify the most impacted areas across the country. And when we talk about open science, I would say what is interesting is that we've developed this algorithm for a specific environmental use case, but we've been approached by the Canton du Valais, so this area, but the archaeological department that was really interested in the information we are generating, because thanks to that, we can help them to identify potential areas where you can find archaeological artifacts, where the snow has disappeared. Then you have these archaeological artifacts that can be released, and it helps to build a new protection plan over the Alps for archaeological protection. So you see, you develop an algorithm for a specific case, but then you never know who will be able to use it for other purposes. Also in the frame of a project that we have for monitoring and building the ecological infrastructure at the national scale, we've been requested to generate different time series of vegetation indices that helps to monitor health and condition of vegetation, and they are freely available now. It's more than 2 terabytes of new data available. It was released in September, if I remember well. And we release all this data using interoperability standards, so you can embed then this data in various clients, such as QGIS, such as the Google Earth or the National Mapping Service at the national scale. Also, a quick example on air pollution. So you remember the COVID crisis, obviously. So back in 2020, this is the situation using Sentinel-5P. This is the NO2 concentration over the country before the lockdown. And then in April, during the lockdown, you see that the level has completely decreased because most of the industry and the cars were not moving across the country. Then next topic, and this is going to be the last example. It's related also to land cover monitoring, let's say. So in Switzerland, the official land cover data set is generated based on an aerial photography interpretation. So we have a grid of 4 million points across the country, where for each of these small triangles, you have a land cover, a land use, and a national nomenclature. So you have the 3 values for each of these 4 million points across the country. But you see that the spatial resolution, when you translate this into a raster, is not that useful because Switzerland obviously is small. So in terms of land cover monitoring, we have to improve somehow the situation. So what we can do, using the Swiss Data Cube, because it provides this huge archive of satellite imagery, together with this data set that is called the aerial statistic in German. So we have 4 data sets of 4 million points during 4 time periods. What you can do, you can use machine learning methodology so that you can extract time series for each of these 4 million points, so that you can then train machine learning or deep learning algorithm and then come up with more precise spatially, temporally, because we will be able to generate a yearly data set, and also thematically, because we preserve the richness of this point. And the initial result that we had, so we just tested over Geneva and the Lake Léman. So we used 1 year of Sentinel-2 images. So we trained random forest models with different classification schemas. We took all the points that we had over the area. So we separate in a training data set and validation data set. And you see that we are already, without tuning the models and so on, so really, I would say, a model that is quite basic. We are already above the 80% classification accuracy. So it means that using these ground truth point together with satellite imagery, we can come up hopefully with some improvement of accurate yearly land cover maps with, let's say, 27 classes across the entire country. Obviously, there are many other applications and potential applications using satellite imagery. This was just some of these many applications that I've highlighted. And just to say that what is important also when you build a data cube is to support your user community of users, but then also to make the data interoperable. So it means both for the upstream services when we talk about mostly the backend, but also the downstream services. So what basically the end user can see, we can use OGC services and other standard ISO standard so that we can really enable an access that is interoperable to these services. So this is the list of services, OGC services we already implemented. We are also testing the new OGC APIs that are already available into a demo instance, and probably next year will be released. And we are maintaining the data cube and updating it on a regular basis. So now we are at the version 1.5, we say, and early next year we will release the version 2.0 of the data cube, improving the interfaces, providing new services, and so on. And really, we think that the data cube technology can support any digital national strategies because it supports innovation and growth in the digital economy. You can improve the efficiency and effectiveness of government investment. You can, at the end, improve management of natural resources. You can stimulate the research. You provide a nice monitoring mechanism. You can generate new informations and provide an easy access and use to different data products. And to finish, I just wanted to talk and to make the link with the open and reproducible science. In that paper in Nature a few years ago, they were asking to researchers if they are able to reproduce an experiment, both their own experiment or the experiment of someone else. And you see in the field of earth and environmental sciences, I would say around 60% of the experiment are not reproducible. So it means that more than half of the experiments cannot be reproduced, so you cannot compare and assess the quality of the results. So one idea to improve that situation is to comply with the FAIR principles. So the FAIR principle stands for the findable, accessible, interoperable, and reusable principle. So it means that we are aiming to provide access to clean data with interoperable standards so that you can facilitate the discovery and access and reuse of this data. So you facilitate the integration of different data sources into various pipelines of analysis. And basically, when you comply with FAIR principles, it's like a data recipe and it's like a cookbook. Then you can just follow the recipe and then you get the same result. So what we have done, we have built also a FAIR compliant national database of your data product where users can easily access and work with these data sets in a very efficient and effective manner. And all the work we're doing, we are trying to really frame it into that spirit. So obviously all the data are open, all the code we generate and the notebooks are usually open, all the scientific research or all the articles are in open access, and also the teaching material we generate is freely available. So we summarized that last year in a publication in Nature Scientific Data explaining our vision for that. And I really would like to emphasize that the vision for us is to become a kind of national infrastructure that we can serve the need of, I would say, any end users in the country. So it will take time, but this is the vision that we have. And if you're obviously interested in this data cube technology, we had a book 2 years ago, edited by colleagues in Brazil, in NASA and Australia, showing the benefit of this technology. And I would like to finish my presentation just to show you that this is really a technology that is spreading all over the world. Now, basically, this map is not the most up-to-date because basically we have Digital Earth Africa. So we have a first continental data cube covering the entire African continent. There is the Brazil data cube that is now operational. We have in Colombia, in Thailand, and obviously in Australia. But we have many countries that are looking with interest to that and trying to develop that technology to support their country. And I would like to really finish saying that from my point of view, also looking at the environmental crisis, if you want to care about the environment, we have to experience somehow the impact of these environmental changes. And I think we are all suffering in a way or another of these changes. But really, this data cube technology is enhancing the scientific accountability and credibility, providing easily evidences, and it helps to build that trust and share knowledge so that we can really discuss with the decision maker. Because without that, obviously, doing science can be somehow difficult. Taking sound decisions can be a big problem, and then at the end, envisioning a sustainable development can be really, really complicated. Just to finish, I want to say that we are open to collaboration, so we are more than happy to discuss with you and help you in a way or another. If you want to follow us, obviously we have our website and all the usual resources related to the internet. And with that, I'm done, and I really would like to thank you for your attention.
Thank you very much, Dr. Giuliani, about the interesting presentation. We have 3 questions for now,
yeah.
And also 1 question for me. I will ask last in the end. The first question is about what is the average process power does it take to apply those algorithms and models at the national level, like the example of Switzerland?
That's a good question. Indeed, this is an aspect that I did not cover. So we used to have the Swiss data cube on a single server, but it was, I would say, quite powerful. It used to have 128 gigabytes of memory and 32 gigabyte and 16 CPUs, sorry. So we were able to process at that period already data at national scale, but the issue, it was a long process. For example, just to generate one NDWI map, taking into account of all images during the summer months, so basically 30, 35 images, or well, multiplied by the number of tiles, obviously, to cover the entire country. It was taking with that infrastructure 24 hours using Sentinel-2 data. So it's long, it's not really competitive if you think about other infrastructure. So what we have done now, and this is the process also for the release of the version 2 of the Swiss Data Cube, we are connected to the HPC infrastructure of the university, where now we have access to 2 clusters of 4,000 cores with petabytes of storage capacities. And I think each cores have something like 512 gigabyte of RAM. So it's a way more easier to work. And just to give you, we took the same algorithm with the same data sets I was mentioning before that took 24 hours to compute. Now we are able to compute the same data sets in 10 minutes. So you see the huge the huge difference. So definitely you need, if you have the ability to be on a really powerful cluster, that would be the best setting, I would say.
Okay, thank you very much. The second question is about the snow coverage. You measuring the snow depth or only the snow coverage? If you're measuring the depth, are you using different satellite images or other techniques?
So we are only measuring in that case the snow cover, not the snow depth, because one of the issues is that we have some measurements across the country, but they are not enough. So I would say the network is not sufficiently dense so that we can come up with reasonable estimates. So this is a big issue. And what also we do, we are not only using optical imagery in that algorithm, but we are also using radar data so that we can at the end also have an estimate on the snow water equivalent, so the snow that is melting basically, so that then this can be useful as an information so that we can then inject that information into hydrological models.
Okay. And the third question is, you presented the example with NO2 nitrogen differences before after the 2022 lockdown, 2020 lockdown.
Yeah.
Are you planning to include more products for Sentinel-5P?
Yeah, this is an ongoing activity that we have currently. So you remember the dashboard I was showing a little bit with the droughts. We are doing the same thing with air pollutions, and basically we have all the different. I think there is 7 or 8 different types of information that you can extract out of Sentinel-5P. So we will routinely generate all this information at the national scale into that platform. And also this is an example I've not shown, but we're working currently with the canton of Geneva, because we have also the Sentinel-3 data. And in terms of air pollution, you maybe know that the dust coming, for example, from the Sahara, we have regular I would say storm with dust coming from the Sahara in Europe, and this dust is basically a nuclear. Basically, the dust act as a nucleus, so that then the pollutants can fix into the nucleus, and then it increases the concentration of pollutants in cities. And basically, the colleagues from the Geneva State, they do not have access to good information related to dust into the atmosphere, but thanks to Sentinel-3, you can generate that information. So you have an information layer in Sentinel-3, and you can provide that information into the model, and then see how the air pollutants behave. So this is currently under testing, but this is also a way you see to integrate, I would say, air quality information for really supporting, I would say, really local applications.
Okay. Thank you very much. About the Swiss data cube, it will be very beneficial in the scientific community. One general question from me. Are you planning to add more satellite data or radio analysis satellite data?
So now we are in the process of ingesting not only satellite imagery, but also aerial photographies, because we have every year the Federal Office for Topography is taking nice images at 10 centimeter resolution of the entire country. So we are about to ingest also this data. And related to satellite imagery, so on a case-by-case studies, we have also ingested, I would say, commercial data from GeoEye and Worldview. So we have, for some regions in Switzerland, we have that data. But we were thinking at one stage also ingesting MODIS data, but because Switzerland is a small country and the variety of landscapes is quite broad, I would say, I don't think MODIS will be really suitable for Switzerland. But if we have the request, then usually we ingest the data, because then we think that, yeah, based on the request from users communities, then this is exactly what we have done with Sentinel-3. at the origin. At the beginning, we were not supposed of imagining ingesting Sentinel-3 data because, as you know, the spatial resolution is 1 kilometer. Well, it's not that useful for Switzerland. But then we realized, based on that request we received from the Geneva State, but still, even if the spatial resolution is not that good, that might improve some local needs. So at the end, we decided to ingest all the data also for Sentinel-3.
Okay, thank you again. Thank you, Dr. Giuliani, about the presentation. Thank you again for joining us. We will be back with our next invited talk after the Christmas break. Enjoy your Christmas break, and we will be sharing the recorded video with you later on today or tomorrow. Thank you again for joining us. Enjoy your day.
Wishing you all the best. And I've sent also to Stelios a copy of the slides in case you want to share them. Okay. So have a good end of the year season. Bye-bye.
Thank you very much.
And see you soon. Bye.